It's crazy.
Alright, today we're going to be your tour guide. You will follow the stick.
Travel Channel Lori.
With the stick. No, I'm kidding. Have you guys seen with the umbrella or the sunflower? Or the umbrella. Follow the umbrella. I follow the umbrella. Here, follow the Hey, push the other.
Steps. 4 steps.
You gotta hold my hand. No problem.
Quite a bit of wind going on.
It feels nicer down here than it does outside.
Not the way I thought it would be. Look at this one here, almost. Well, that's their version of a rivet. That's crazy.
To move the river from the construction site. They did that by building 4 diversion tunnels. There's 2 on the Arizona side and 2 on the Nevada side. They're 50 feet diameter, about 3/4 of a mile long, and it did take them almost 2 years to completely blast out all 4 tunnels. Once the tunnels were finished, they had to figure out how they were going to move the river into the tunnels, and they did that by building 2 coffer dams. A coffer dam is a temporary earth-filled dam. So one was built upstream, and that pushed the river into the tunnels. The other was built downstream, and that kept the river from flowing back into the construction site. So once those coffer dams were finished, they drained the site, and they removed 135 feet of loose rock and debris to get down to the bedrock, which is the dam's foundation. June 6, 1933, they were ready to begin building the dam. They had buckets carrying 8 cubic yards of concrete, which is 16 tons. Those were delivered every 78 seconds, 24 hours a day, 7 days a week for the next 2 years. Once they were finished building the dam, then they were ready to begin filling up the lake. And they did that by closing off 3 of the diversion tunnels by lowering heavy steel gates, and they did leave 1 tunnel open. That way the river could continue to flow back downstream. So once the water was high enough, they did close off that last diversion tunnel. They blasted out the lower coffer dam. That way the river can move more freely downstream. But the upper coffer dam, it still remains underwater today. It took a total of 6.5 years to completely fill up the lake. So how do we get the water from one side of the dam to the other? Intake towers, and there are 4. 2 on the Arizona side and 2 on the Nevada side. They're 395 feet tall, and they do not sit on the canyon floor. They sit up on 250-foot rock ledges. So the water flows down through them into 30-foot diameter penstock pipes like the one that you see out the windows. You may feel the floor vibrating beneath your feet, and that is up to 96,000 gallons of water per second flowing through the pipe. That's enough water to fill an Olympic-sized swimming pool in just 7 seconds. Then the water flows down into smaller 13-foot diameter pipes that leads to the generators, spinning the turbines, and then it flows back down the river. Last thing I'm going to tell you about are the spillways, and they're on either side of the dam, one on the Arizona side and one on the Nevada side. And they were built to keep floodwaters from going over the top of the dam. We've used them twice. Once in 1941 for testing. Thank goodness they worked because we did use them again in 1983 after a heavy snow melt in the Rocky Mountains. That is where 96% of our water comes from, and we do have a picture from that flood of 1983. During that flood, water went over the spillways for 63 days in a row. That's the equivalent of 2 Niagara Falls, and the water did come up about 7 feet from the top of the dam.
No, was there really
Yeah. Except it's much warmer here. It was freezing there.
On behalf of the Bureau of Regulation, welcome to the Nevada wing of the power plant. I would like to direct your attention down the road to the generators. There are 8 leaves here on the Nevada side. We have 9 more on the Arizona side for a total of 17 generators. Each generator stands 70 feet tall, but you can only see the top 30 feet of them. If you look at this first generator right here, N1, which stands for Nevada 1, you look about halfway down, you are going to see a light shining on a 65-foot steel shaft. At the bottom of that shaft is the turbine. The water comes down through those huge penstock pipes, hitting the turbine at about 48 miles an hour. The turbine spins, spinning the shaft, which is connected to the rotor, which is housed inside that red drum. The rotor is made up of 40 electromagnets or poles, each one weighing 4 tons. All around those magnets is about 2 miles of copper coil. The rotor spins at 180 revolutions per minute. Just one generator can produce up to 130 megawatts of electricity. That's enough to power about 65,000 homes. If the lights on top of the generators are on, they are producing power. Next, if you look down at the power plant floor closer to us, you will see a small rust-colored Pelton water wheel enclosed within a fence. This is a smaller generator that provides power for our in-house use here at the dam, such as for lights, elevators, and machinery. And we do have one just like this on the Arizona side. These smaller generators produce 2.4 megawatts of electricity. Now, if you look above the generators towards the ceiling, you will see 2 P&H bridge cranes going across the room. First one has our American flag hanging from it, and we do have 2 more just like these on the Arizona side. These original cranes run on tracks and can be moved the entire length of the power plant. Just one crane can lift 300 tons. To put that into perspective for you, just one of those cranes can lift the Statue of Liberty, which weighs in at 225 tons. But sometimes that's not enough for what we need here at the dam. They must be used together to make a super crane, which can lift over 600 tons. Because if they need to work on one of the rotors and lift them up out of the generator, those rotors can weigh over 560 tons. Now, if you look down at the floor around your feet, you will be looking at the terrazzo marble that was put in place in 1937 by the Martina family with visitors in mind. It was at a cost of just under $60,000. If you were to replace this floor today, it would be well into the millions. The marble flooring covers 121,000 square feet of the power plant floor. Also on the floor you see symbols. They were created by American artist Alan Tucker Drew, who wanted to bring Southwest Native American designs into the project. The one I'm standing next to shows an electrical outlet which represents power. And the circular one behind the rest of you shows the movement of water flowing through a turbine, power and water. And now, if you look behind you or to my right, you will be looking in the direction of Lake Mead. Between Lake Mead and us, right behind this wall, is the Hoover Dam. It stands 726 feet high, 45 feet wide at its crest, and is 660 feet thick at its base. So to help you visualize this, if you look from this wall all the way right down this room, that is 650 feet long. So if you were to add just 10 more feet, that would be the equivalent of the thickness at the base of the dam.
Or you want to create some electricity?
They still, I mean, it works, right? You know? Tesla was a genius.
Oh, this hurts my nose so bad. Is everything on?
Everything's on.
See, it's a lot smarter for them to use water to spin that thing, isn't it?
And dry.
Yeah.
So is that basically a valve they can open and shut it?
Yeah, that butterfly valve, they can control it and bring it around, and then
Or
that's
limit
probably
the flow and everything?
Yeah, there's your turbine right there, and I'm sure
So what does that do for it? Like,
when it spins, it makes your magnetics go back and forth. You know,
okay.
probably, and then it starts generating. Only thing I don't know.
That's the turbine. That's the inside of the turbine.
Yeah.
So
The only thing I don't know is like what voltage it puts it out on when it spins. You know.
Or they have to convert
most
it?
high voltage transmission lines are 56 kV.
56. I didn't know
Yeah,
what.
56,000 volts is your basic overhead power transmission lines.
So which one is the, oh, that's the water goes,
That's what
that's
actually turns
goes
it.
out.
Yeah, and then that shaft comes up, and that's what spins it.
Yeah, I think she
I
said
might do.
that.
I don't know.
Yeah, the shaft is what we saw from up top, and what we all saw was from the fence up, basically.
Yeah, we're looking just at that part there.
Yeah.
Why does the shaft have to go so low?
The dam. It is the oldest and largest continuously operating cableway crane system in the world with a lift capacity of 150 tons. The crane is used to deliver large equipment from the road to the ramps below. Looking at these canyon walls, one can marvel at the tenacity, courage, and skill of the fearless men that performed some of the most dangerous undertakings on the Boulder Canyon project. These brave characters, called high scalers, swung from the top of the canyon walls by a single rope on a bosun's chair, drilling, blasting, and chipping away at the rock. They worked the walls to their solid foundation to prevent the natural rock from falling on the workers below.
Hey, John, what's up?
What's over there,
Josh, you look at that new visitor center, how much a fee it was just to build it.
Right there?
Yeah.
Yeah.
I don't know why it just dawned on me that that's just how we're into those lines.
When we go to
Yeah. Oh, yeah. No, you can't remember everybody. Yeah, I do the same thing. Our loved ones will be like, yeah, look, years ago you worked on my side. Hey, do we need to come down and get you in the car? Or?
Names of the other.
They broke That's how the toes they rubbed off.